Hello everyone and welcome to a talk about translating Lambda calculus into C++ templates. My name is Vít Šefl and I'm a PhD student at the Charles University in Czechia. So, first of all, I'll try to explain why would we even want to translate anything into C++ templates, let alone Lambda calculus. So, templates were added to C++ to facilitate parametric polymorphism. That is, writing a piece of code that can handle values of different types without depending on the properties of that particular type. The same mechanism can be found, for example, in Java and C# under the name generics. In the case of C++, when you define a class or a function, you can include a template declaration which allows you to abstract some type. When you want to use the definition, you just pick a concrete type and the compiler will generate the appropriate class or function. The templates can also abstract over a list of types and even some integral values. However, the template system is more powerful than it was originally designed for. If you combine templates with other C++ features, such as the using keyword, you can describe arbitrary computations. And since templates are only ever present during the compilation, this allows you to force the compiler to perform compile time computations. This technique is typically called template metaprogramming. Here's an example of how this works. We define a template class named if, which is parameterized by a boolean and two types. Then we have two template specializations that tell us what to do depending on the value of the boolean. In the true case, we simply define an inner member called type as the second parameter. In the false case, we define an inner member called type as the third parameter. Once we have that, we can instantiate the template with some boolean value and of course the two types, and the inner member type will contain the result. In particular, this piece of code compiles because the type of the variable 5 is an integer and thus the initialization is valid. Now, this all looks like a neat trick, but you might be asking if this is actually useful in practice. In the past, template metaprogramming was used to evaluate various optimizations, such as unrolling loops, moving computations of constants from runtime to compile time. However, more recent features of C++, such as the const expr keyword, have made template programming obsolete in this area. Another popular use of template metaprogramming is in generic programming libraries. These libraries typically need to manipulate types, access type traits, and similar. These techniques are still rather poorly supported by the C++ standard, despite the fact that they are used even in the standard library. For example, the previous if metaprogram is something you can find in the standard library under the name std conditional. Another commonly used metaprogram is std is same, which performs type equality. Okay, so now we know what template metaprogramming is and why it's important, hopefully. So let's take a look at some common issues with the template code. Here's an example of a more complicated metaprogram. If I didn't put the name of the program into the example, it would be quite hard to even guess what the program is doing at a first glance. You can notice there's a lot of random keywords lying around the code, template, type name, class, and so on. There are some double colons and similar. Now, let me highlight the parts of the code that actually perform useful work, in the sense that they contribute to the semantics of the metaprogram. If you squint a bit, you should now see the familiar definition of the list filter function. There's an empty list case, which simply returns the empty list. There's also the non-empty list case, which recursively filters the rest of the list, and if f of a was true, it adds the value a back to the front of the list. In this particular example, the boilerplate code is roughly 2/3 of the entire metaprogram. In general, you can expect at least half of the code to be boilerplate. Another common problem is error messages. I've taken the previous code and introduced a rather common metaprogramming error. If we compile the code with GCC, we'll get this rather puzzling error. So GCC is complaining about the second template argument of the std conditional metaprogram, and is complaining that it is not a type. But if you look into the node, you can see something that looks like a type. So why is GCC complaining? Well, the issue is that I've removed one of the type name keywords. By default, C++ assumes that when you refer to some inner class member, you are referring to some value and not a type. And this is the reason why you need the type name keyword to let the compiler know that you are going to refer to a type. This is a fairly common error in template metaprogramming. Now, I'm not the first one to attempt to solve these issues. There are C++ libraries that deal specifically with template metaprogramming, such as BoostMPL or its successor BoostHANA. However, you still write a rather weird C++ code with these frameworks. However, at least the error messages are better and the code is more comprehensible. However, if you want to avoid writing weird C++ code entirely, you'll have to reach for a different tool. Here I've used the translation label, but there are many different tools under this label, but they all share the same basic idea. You describe the metaprogram in a more fitting language, and then use the description to generate the template code. The source language doesn't need to have any boilerplate code, and the boilerplate code can be added automatically during the translation. Note that you are not limited to just third-party tools such as transpilers. You can even use a translation with something like C++ macros or even other metaprograms. So, what's a good choice for a language to describe these metaprograms? From the previous examples, it would seem that template metaprogramming is some sort of functional programming. And indeed, you can think of templates as type-level functions. Thus, the inputs are the template parameters, and the output is the defined member, which in this case was called type. Similarly, metaprogramming data is represented by classes, and since classes are immutable, you cannot go back to a class definition and mess with its members after it's been defined. That means that data in metaprogramming is immutable. There are also no loops, if statements, and similar. Doing anything interesting pretty much requires recursion. We should therefore use a functional language to describe these metaprograms. The translation then takes this functional program and transforms it into a C++ template code. We can optionally also have a type system to help with error messages, but I'll get back to that later. So, my main contribution is a new method of translating Lambda calculus into C++ templates. It should also allow for the translation of common features found in functional programming, such as algebraic data types and recursion, since we generally don't want to program anything in pure Lambda calculus. There are other existing translation methods, but I wasn't particularly satisfied with some of the choices those methods have made. So my focus was primarily on the ease of use, extensibility, and clear non-strict semantics. In particular, the resulting metaprograms should still be readable by humans, so they can be manually adjusted if necessary. The translation should be extensible, in case we want to add support for, say, partial functions or more fine-grained strictness control. And of course, we should be able to use the resulting metaprograms with existing code, in particular the library metaprograms. And laziness is going to help the compiler by removing some unnecessary template instantiations. So, here you can see a part of the translation, in particular the translation of Lambda calculus. We have three different cases, one for variables, one for abstraction, and one for application. I don't want to go into too much detail here, so I'll just point out that the translation is simply a traversal of the abstract syntax tree, and the generated code resembles the metaprogramming examples given before, though there are some minor differences to accommodate higher order functions. If you're interested in the details of the translation or the translation of the other features, I encourage you to check the paper. Now, let's take a look at some examples. I'll be using Haskell as the input language, but the translation is not limited to Haskell in particular. We have a successor function, which simply adds 1 to its parameter. We have a higher order twice function, which applies the given function f to some argument twice. And we have a constant named 5, which uses the previously defined functions successor and twice. Of course, we apply the successor function twice to the number 3, we expect the result to be 5. If we translate this code into C++ templates, we'll get these 3 structures, which all contain an inner member called type. This is going to be the result of the computation. If you ask the compiler, it will tell you that 5 type and int of 5 are the same types. You can check this by using the std is same metaprogram. You can furthermore access the results value, which is an integer compile time constant. This is actually fairly important because you can then use this value in other compile time only contexts, such as when defining bounds of an array. So, I mentioned before that the translated metaprograms should be evaluated lazily. You can put this to the test by defining 2 variants of the const function. K1 is a const function which uses its first parameter and ignores the second one. K2 uses the second parameter and ignores the first one. We also define the AP function, which applies its parameter f to a terminating and a non-terminating computation. The terminating computation in this example is simply the number 1. The non-terminating computation is a simple infinite loop, let x equals x in x. Again, translating this code into C++ templates gives us 3 different structures. The inner member type is again the result of the computation, but compared to the previous example, the results are now also functions. These functions have an inner template named apply, which can be instantiated with the actual argument. In this case, we instantiate the inner functions with k1 and k2. In the first case, if we apply the AP function to k1, we get the expected result int of 1. So the computation finishes and we get the result 1. In the second case, we apply AP to k2 and we won't get any result. In fact, we'll get a compilation error. The compilation error here is represented by the bottom symbol. The actual compiler error can be seen here. I've only included the relevant part of the error message. The error message is quite long. You can see that GCC is complaining about reaching some sort of template instantiation depth limit. Instantiation of a template can lead to instantiations of more templates, and to prevent the compilation from hanging, C++ compilers place a practical limit on the depth of these nested instantiations. You obviously don't want your compiler to hang when given some malicious code. However, some valid metaprograms might hit this limit, and for that reason, most C++ compilers allow you to change this limit. In this particular example, we can see that GCC suggests using the flag -f template depth to increase the limit. The translation also handles algebraic data types, which includes both the constructors and the case analysis. Due to the time constraints, I'll just give an example of the construction. If you are interested to know how the case analysis works, you can find the details in the paper. We have a standard definition of lists. A list is either a nil, an empty list, or cons, a non-empty list. We also have a function named countdown, which creates a list of numbers starting with the given number and counting down to 0. The constant numbers is a list obtained by applying the countdown function to the number 2. So this list should hopefully contain the numbers 2, 1, and 0 in this order. If we translate this program, we get the usual structures called countdown and numbers, but we also get a templated structure named cons. Notice that the structure itself doesn't contain anything useful. Only the template parameters are used to store the values of the 2 fields of the constructor. Similarly, we also have one structure named nil, and since the nil constructor doesn't have any fields, the resulting structure is not a template. There are no template parameters to store the fields. We can now check that the numbers list contains what it should. If we force the compiler to perform the computation, we do that by accessing the in-member type, we can see that the result is indeed a list which contains 3 const cells with the numbers 2, 1, and 0. This is the standard representation of lists. And a final example shows how the translated metaprograms might interact with existing code. In this example, we want to use the library function std_isPointer with some filter metaprogram. The problem here is that the filter metaprogram is obtained by applying the translation, and the isPointer metaprogram from the header type traits uses a more direct implementation. This means that these two metaprograms are not immediately compatible. In fact, you will get a compile error if you try to use these. However, we can fix this by creating a fairly simple adapter. In this case, the adapter is a metaprogram called predicate. It takes a unary predicate from the standard library and returns a compatible metaprogram. Essentially, it converts the standard library predicate into a type-to-bool function. We can then apply the predicate metaprogram to std_isPointer and use the result as usual. Now, I've mentioned that the type system in the source language is optional. While the translation makes a lot of errors impossible, such as missing keywords, it cannot prevent the user from making silly mistakes, such as using numbers as functions. If that happens, we'll get a slightly ugly compilation error. In this case, the error message isn't too bad. We can see that the code is trying to use some template called apply, and the template does not exist. This suggests that it's trying to use something that is not a function as a function. However, in a lot of cases, the error message is going to be less helpful. In particular, these error messages have the tendency to point to symptoms rather than the causes. If the source language goes through a type checker first, you might get an error message such as 5 of type int is not a function, which is clearer and more readable and can help pinpoint the issue much better. In fact, there's interesting information about the translation. If the type system does not allow the programs to quote-unquote go wrong, the only compilation errors that you will see from the result metaprograms are the ones from hitting the template instantiation depth. So, to summarize, compile-time computations are gaining support in C++, but type-level programming is still verbose and error-prone. We can avoid these problems by describing metaprograms in a different language and then translate back to C++ templates. This way, we can write succinct programs and the boilerplate is added by the translation automatically. In this talk, I've given an overview of a new translation method that focuses on clear semantics and simplicity. The translation itself can be used in libraries, as macros, or in higher-order metaprograms, or it can even be used in third-party tools such as transpilers. And finally, an optional type system can be used to catch even more errors before the template code is even compiled. And that's it. Thank you for your attention, and I'll be taking questions now.
Hi, well, thank you very much for your presentation. It was an impressive piece of work. I think it's not easy to implement Lambda calculus with C++ templates, and it seems that you have done a great job there. I see no questions in the Q&A section yet, so I'll have a question. It's very impressive what you did with these templates, but if your only goal would have been to do Lambda calculus, then I'll think that there are better tools to do Lambda calculus. So can you expand a little bit on what you want to do and what you want to achieve with these Lambda calculus things in C++ templates? because, yeah, what I said, the only goal can't be to do lambda calculus because I think there are better tools there.
Well, in particular, I was interested in automating some of the process of writing these metaprogramming libraries, because a lot of these libraries have familiar functional code, such as these filter functions, faults, and similar. And it's basically just rewriting, like you take a code from, let's say, Haskell, and you basically just rewrite it into these templates. The process is fairly manual, or the process is fairly mechanical, but you still need someone to do it. And there's obviously a lot of space in which you can make mistakes. So the main goal was to automate this process. Ideally, you could just take some code in Haskell, perhaps compile it down into GHC core, and then take the GHC core, apply this translation, and get a whole new library that you can use in C++ to use in these metaprogramming frameworks.
Okay, and do you have already experience in how this compares to the old-fashioned way to do it? I hope that you achieve improvements and that it's clearer or less error-prone or compactor or whatever.
Well, it is definitely less error-prone because when I tried, I wrote a tool which uses this translation, and it translates from something like a Haskell. It's not exactly Haskell, but it's a Haskell-like language with a simple type system. And just having the type checker behind you when you are writing this code and ensuring you do not get any weird compilation error messages when you then attempt to use these programs is a big help. I cannot really speak for efficiency because I'm really just trying to write those programs as they would be written by humans. So there are like no crazy optimizations that would make the program maybe more opaque to the actual user. So it's still something that is supposed to be readable. But in terms of template instantiations, it's about the same as the existing standard library code.
Okay. There's one attendee who is a guest now and wants to raise a question. So the floor is yours.
Hi, thank you. So thanks for the presentation. It's been a while since I used C++, but I recall that telling the compiler if something is const has always helped the C++ compiler generate more efficient code. And is that something that this kind of translation can do? I mean, intrinsically, all the functional programs are immutable, so I guess maybe it could just automatically put const everywhere in front of variables and stuff like that.
Right. Thank you for the question. So this is perhaps a slight misunderstanding of what this tool is actually doing. It's allowing you to describe metaprograms which are entirely compile time. So you can then use the metaprograms in other situations, but the whole computation or the whole use of these metaprograms and the translation happens entirely at the compile time. So if you, for example, use the metaprogram to compute some constant and then compile the resulting C++ code into machine code, you are almost certainly going to find just a constant in the binary section, like in the binary. There's not going to be any computation. There's just going to be, okay, load this constant into your register or something like that.
Right. I was thinking about if you describe a computation and the resulting program. I mean, how should I put this? So in the end, you get some kind of program that does something useful. I mean, the metaprogram describes it, and when you use that metaprogram in your actual code, you instantiate it to something with actual types, and then you get something that does something, like handles strings in different ways, with characters or wide characters or something like that. And so in that end result, you would want const in the appropriate places. But maybe you're right. I'm not understanding fully what.
No, it's fine. Like I understand what the question is about. It's more that this is more like an accidental feature of C++. So there are basically two languages in C++. There's a normal language that you program in, and you describe programs that actually compile into some code that then runs on your machine. And then there's this other weird language, which I here call template metaprogramming, which is entirely like done during compilation, and there is basically almost no interaction between these two. The only thing you can do is you can compute some constants in the template metaprogramming, and then you use these constants in the other piece of code, like in the actual runtime code. So there is not a lot of room for these sort of interactions, but what you can do, and this is especially useful for let's say library authors, because they can write some code which is generic, which you can use then with some user-defined data types, and still get this efficiency because, okay, the compiler can compute some constants which are relevant for your user-defined data type, and then optimize the implementation of some library function or some library data structure based on your user-defined type. But that's more like a higher level use of template metaprogramming rather than of the translation itself.
Okay, with an eye on the schedule, I'll propose to stop this discussion here and to continue it on the coffee tables, which are available. Thank you once more for your presentation, and thanks everyone in the audience for their presence.